In this video, we are going to talk about sequential modular approach basics. So we'll revisit the basics of sequential modular approach. We'll identify two major issues with sequential modular approach, namely partitioning and tiering, and how to deal with them. And as such, why these two issues would arise when you want to simulate a process with the help of a sequential modular approach based process simulation. So the basic philosophy of sequential modular approach is that you give out input, give the values for the equivalent parameters and generate the output. Because for each module, the model equations are written, energy balance, mental balance are already written, and you get the exit or output. If there is a recycle stream, then you have to deal with it, because in that case you have to iterate upon the simulation. So basically, I have a flow sheet or a unit operation. I provide input, I provide conditions for the operations and equipment parameters, and I get output. This is basic philosophy. And in any SMA, a unit module is self-contained. It is not dependent on any other module. However, two different modules are dependent, may be dependent on each other. The downstreams are dependent on the upstream through the output this generates. Sequential modular approach, is most efficient for a flow sheet which is acyclic. That means there is no recycle. However, you will seldomly find such flow sheet in process industry. Whenever there is a recycle, you have to tier at least one stream so that it becomes acyclic. More the number of recycle, more number of tiering is required, and lesser will be the efficiency of the simulated process. So whenever there is a flow sheet with recycle, say for example you got unit 1, 2 and 3, and this is recycled back to unit 1, you have to tier one stream. What I mean by tier, you have to provide an initial guess for one of the streams, because what is the principle here? If I want to solve unit 1, I require this input. So unless and until I have this input, I can't solve unit 1. And if I can't have this, I cannot generate this, I cannot generate this, and hence I cannot solve this flow sheet. So I have to tier one of the streams, supply initial estimate for that, and then I have to keep on updating it till I get the convergence. So when I say you provide initial case, what you have to supply is flow, composition, temperature and pressure. So even composition are dependent upon the number of compounds present in the stream. Because of that, what will happen? Multiple pass calculations and must solve a system of nonlinear equations to converge the TS stream. So whenever there is a TS stream, it becomes multipass, and you have to solve a system of nonlinear equations. There would be so many equations, so many unknowns, all of them non-linear in nature. So you have to solve it, not you, the simulators. Advantages of SMA, as we might have discussed, it's very simple as far as its concept is concerned. It's very easy to understand, it's very well defined, and there are no ambiguity. It corresponds to physical structure. Reason being, it is a modular approach. A distillation column will look like a distillation column. If you write a mathematics, distillation column will look like a maths problem. A pump is like a pump, a heat exchanger is like a heat exchanger. So you can relate it with what you are drawing in your pen and paper, and it requires less storage and capacity or memory of the computer. However, some disadvantages are that there are no direct way to handle design calculation. You have to iterate upon. In the same way, you cannot solve an optimization problem directly. You might need to do iterations on that, and it's not efficient for flow sheet with recycling. Most of the commercial steady-state simulators, they use this approach, that is SMA. And Aspen ISIS is a very good example. Just like Aspen ISIS, you have got ChemCAD, you have got Aspen Plus, you have got Design 2, and there are so many. And all of them, they are having two issues whenever there is a recycle. One, you have to partition the flow sheet and you have to tier the flow sheet. What I mean by partition? Partition is you have to say that, okay, my entire flow sheet is having 15 units, and out of 15 units, say for example, I'll solve first 3 units together, then 4, 5, 6, then 7 to 10, then 11, 12, and then 13, 14, 15. So there has to be partition, and for every partition you have to solve a flow sheet. You might need to solve a flow sheet using a tiering, or tiering flow sheet. So we'll be able to see that as we proceed further. Let us talk about partitioning and tiering and why they appear in process simulation or flow sheet simulation. So if your flow sheet is acyclic like this, where you have mixture to reactor to heat exchanger to flash, and these are your product, that's it. So you got S6 and S7 as a product, 100% conversion over here, no recycle, and you're happy. And the simulator also is happy because the computation sequence is very simple: mixture to reactor to heat exchanger to flash. But if the system is like this, that there is some unreacted compound, which is the case, which is coming back to the mixture and then it comes back to the reactor, and this keeps on hovering around, means you have a recycle. And the moment there is a recycle, sequential modular approach has a problem. What kind of problem it has? As per the philosophy of sequential modular approach, if I want to solve reactor, I have to solve mixture first. If I want to solve heat exchanger, I have to solve reactor first. If I want to solve flash, I have to solve heat exchanger first. However, the output of flash goes to mixture. So in a way, if I want to solve mixture, I have to solve flash first. And if I have to solve flash, indirectly I have to solve mixture first. So it's a cyclic process. Cyclic process cannot be handled in sequential modular approach. So you have to make it acyclic. How to make it acyclic? Either tier S3 over S4 over S5 or S6. Out of S3, S4, S5, S6, any one need to be tiered. The moment you tier it, the process becomes acyclic and you will be able to converge it. So in this case, S6 is a recycle stream, and if I tier the same stream, right, then I have to initiate that stream x0 considering the initialization of S6. So what do I need to initialize? I need to initialize temperature, pressure, composition and flow. I forgot to mention flow here, but the flow also is a part of initial estimate. Until what you will be converging? Like till what you will be iterating? Till x0 S6 and x1 S6, that is the one which is estimated and the one which is calculated, they are in the same range of the values, like same temperature both the sides, same pressure both the sides, same composition for all the species both the sides, and same flow both the sides. Now it may not be exactly same, you can provide the accuracy, but still you have to convert so many variables. So imagine that there are so many equations, so many variables to be converged simultaneously. So naturally it is a computationally tough task. How do you do that? There are two ways. You have to use a convergence block and you have to use a numerical method. What do I mean by a convergence block? See, this is the recycle stream, right? So I can identify that S6 is a recycle stream. HYSYS, or for that matter any particular simulator, will not be able to identify that this is a recycle stream or this is a TS stream unless and until you put a control box. So there is a convergence block. So in HYSYS there is a convergence block named R. So it will be a recycle block. So you have to put that R here. And what happens is a part of S6 becomes an input to S6 and the remaining part becomes output of that. So there is a R block, input to that is S6 and output is S6 dash. Right, so this is input and this is output. So this is a block. So this is a convergence block. So in HYSYS it is termed as a recycle block. And another thing is numerical methods. So within that block there are so many numerical methods which are available to you. The default might be used, but if you want to change, you can change. You can also change the accuracy level you want for temperature, pressure, flow, composition, whatever. These are commonly used numerical method: Weierstrass method, Newton-Raphson method, Brodman's method. You can select the one which you want, right? It will update the temperature, pressure, composition and flow. Now when you want to converge, recycle, the iteration has so many equations, so many unknowns. There is one more way where you can have this, and we'll see that as we proceed further. Before that, let us see the sequence when you have S6 as a TS stream. So you start with S6, tiered S6, mixture, reactor, heat exchanger, flash and update S6. So what I mean is this: tiered S6, mixture, reactor, heat exchanger, flash, update S6. Keep on doing this till two successive x0, x1 are same. And as I told you, it is not necessary. It is that S6 becomes your TS stream. It can be S3, S4, S5, any one within the loop. It can be this, this or this. It can also be TS stream. Recycle stream is S6, but tier can be any according to our knowledge, according to our knowledge of the process or our ease. We'll see that as in some future time. Right, so when a model is complex with many recycle stream, it's not possible to eyeball the flow sheet and come up with a TS stream. So here you can say in this flow sheet you can say that okay, I have got one recycle and my tier could be one of the S3, S4, S5 or S6. So that I can see. However, if the flow sheet is not simple, I can't do that. Right, now this I can consider it as still a simple flow sheet. Let us first discuss this. So there are two critical issues facing in SMA. One is minimum number of TS stream and their locations, and two computation sequence. So how many numbers of TS streams are required and which are they, that is important, and the computation sequence of the process. We'll discuss about this later. So if I see this as a process, there are two loops which are taking, there are two streams which are coming back, so S7 and S6. So there are two recycled streams. And how many TS streams? In this case, two. But which are them? There are two TS streams. So which are they? Like I have mentioned here, S6 and S7. So these are two recycled streams, but they are not necessarily the TS stream. I can have S3 also as a TS stream. So when I take S3 as a TS stream, this loop is broken. So along with S3, I can take either S6 or S5. So there is S3, S6 is one combination of TS set. S3, S5, another combination of TS set. Same way, S5, S7, one combination. S5, S3, another combination. S6, S3, one combination. S6, S7, another combination. So if I combine all of them, there will be 4 sets, out of which I can choose any one for tier. Right? So here I got 2 recycled streams and I got 2 TS. If I go to this flow sheet, how many recycles are there? 2. Recycles are 2. S6 coming back and S7 coming back. How many TS streams? Now see, there can be multiple answers as I told you. So yeah, one possible reason is, one possible set is either S3 from this loop and S5 from this loop. But if you observe properly, you see that S4 stream is common to both the loops. S3, S4, S7 and S4, S5, S6. So if I tier S4, I am breaking both the loops, and if both the loops are broken, the flow sheet becomes acyclic. So I just can solve this problem by just tiering one stream, and that is S4. Right? So S4 is one stream. Like what will be the sequence in that case? S4 tier, S5, S6. Right? Then S4, S7. So this. So I get S3. And I got S4 back. So this is how I can solve this. So by sequence would be S4, B3, B4, B1, B2, update S4. But if I'm not going with S4, I may go with S7. Then in that case, what will happen? I'll need 2 streams. S7. So I'll be able to solve B1 because I got S7 updated, S7 tiered, S3. But I won't be able to solve B2. Reason being I don't have S6. So if there is S7 which I am considering as a TS stream, another TS stream is S6. So I'll start with S6, S7, then I'll solve B1, then B2, then B3, and I update S6. So likewise, for any given flow sheet, there can be more than one set of TS streams, and it is quite possible that when there are some streams which are common to the loops, one or more loops are being broken by them, and that is why we say that number of recycled streams and number of TS streams are not only equal, they can be less. So number of recycled stream can be maybe always, it will be always right, greater than or equal to minimum number of TS stream. So if there are 2 recycled stream, we may have 2 TS stream, but we may have 1 TS stream as well. So this equation is number of recycled streams greater than or equal to minimum number of TS streams. Is it making sense? Okay. But this somewhat complex flow sheet, and like they say somewhat, but it's quite a complex flow sheet. We can't identify which are your TS stream. If you spend some time, you may be able to say that okay, this many recycle, but you won't be able to say that which are the TS stream. So yeah, looking at this, since the answer given is 5. Right, so I have got 5 TS stream here. So which are those? I need to check. I just can't say randomly that these are my 5 TS streams. So when there is a flow sheet which is complex, there are some algorithms which will help us to identify which are my TS streams. And this may be again a part of a flow sheet. It may not be the entire flow sheet as well. So talking about this, we'll identify TS streams, and whenever there is a TS stream, you require iterations. So these are my summary based on recycle that I have to find out first how many TS stream, that is number, and this will be less than or equal to recycle stream. 2, which are those TS streams. So I have to identify and put those blocks there. Which convergence method I am going to use and in which order I am going to solve them. So that is partitioning. We are going to see what partitioning is maybe in the next video. Just like recycle creates iterations, there is another type of convergence problem whenever there is a design specification, whenever there is a feedback control kind of problem. So in this case, say for example, my heat exchanger temperature, right, is is governing the purity in S8. So if I want to maintain some specific purity in S8, this is my product, one of the product of flash, I must maintain temperature here. So that becomes a loop. So what I do is, what is the recycle information here is the composition. See, the difference between this stream and this stream is that this contains every variable, temperature, pressure, flow, composition, whereas this contains only one variable. That's why this is called as non-standard stream. We have discussed this in one of the videos. So this is a non-standard stream, and this comes back to this, and these loops will also require iterative method. However, this will be lot easier to converge compared to TS streams because it involves only one variable, and the composition relation between temperature and composition is explored. That's it. So having discussed this, our next target would be to discuss partitioning and precedence ordering, which I think we'll see in next video.